Last class we talked about PWM converters using AC to DC converter, that is using thyristors and phase control converters. There we require for turn on and turn off of the thyristors, especially turn off. Turn on we can give gate pulse, to turn off we have to give force commutation. So, we will study a very popular force commutation of thyristor, and this force commutation we will study in the context of a DC to DC converter, that is a chopper. So, let us talk about DC to DC converter. It is a very popular scheme used before by thyristors, used for thyristors for commutation. So, DC to DC conversion. Here the circuit, let us say this is our input, let us say this is our battery. Okay. Then you have the thyristor, main thyristor to be commutated. This is a basic buck converter configuration. This is your freewheeling diode, DFW freewheeling. Then you have the motor load here. Okay. For force commutation, for turn on this device, we can give a gate pulse here. Thyristor will be turned on. So, this will talk about switch 1, S1. S1. Now, to turn off this thyristor, we will give a reverse bias across the thyristor by from a charged capacitor. So, this is the capacitor to give. Okay. Initially, this capacitor should be charged. It will be charged through a resistance. This is the switch, then a resistance. So, during turn on of the chopper circuit or DC to DC converter, first thing is you have to turn on this switch S1, SW, such that the capacitor will be charged to input voltage E. Let us say this is E. So, knowing the R and C, we know the approximate time constant. So, through a mono short, we can turn on this switch and after that we can switch off it. So, by the time capacitor will be charged to this voltage here. Now, but this is not the voltage we have to apply across the thyristor. For thyristor to turn off, we have to apply, we have to reverse bias. That means anode should be negative compared to cathode. That means we have to reverse the capacitor voltage before the thyristor can be turned off. So, there is an auxiliary resonance circuit we will be using it. This is the resonance circuit. It constitutes one diode, then L, that is the resonance circuit, comes across this one. This diode is given, this LC will act as the resonance circuit such that the diode is given such that once the capacitor charge in the opposite direction due to LC is no discharge. So, there is no reverse conduction. To block the reverse conduction, we have given this diode D. So, this capacitor C will be charged. So, L and C will act as the resonance circuit. Okay. Now, there is another auxiliary thyristor is there. This is this one. This will call us S2. This is, if this is S1, this is S2. S2 will mark with a different color so that it is visible. This is S2. Okay. Now, how the chopper works? This is a buck converter. That means we can have voltage less than DC voltage less than the input E voltage, variable voltage. So, this is a DC to converter, buck converter. So, this whole thing will act as the commutation circuit. including the switch S1. So, as I told, the first thing is 1 to start on. Turn on SW for a small period. This period depends on the time constant RC of the system. So, that capacitor will be such that the capacitor is charged to E, such that initially the capacitor is charged as shown in figure. Capacitor is charged to E as shown in figure 1. So, let us talk about this is figure 1. Okay. Now, capacitor is charged. Now, we are ready for turning on this chopper. So, now we are turning on the chopper. First, this is only the initial charging process. Now, once this capacitor is charged to E here, the chopper is ready for action. Now, S1 is turned on, 1. S1 is turned on. S1 is turned on, what will happen? Immediately this E will come across the DF. So, DF is reverse biased and E will come across the load side. This E which is coming across the load depends on when we are, the duration depends on when we are turning off S1. So, first let us say we are turning on S1. So, how the circuit will be? See the circuit I will draw here. You have E here, that is E here, thyristor is turned on. So, this we will say this is a turned on switch, this is on, S1 is on, diode is reverse biased. So, that will not come into picture. You have this load. Okay. Now, there is a capacitor here, charged capacitor in this direction, and there is this diode and L. So, moment it is turned on, the load is we want the load is a DC circuit. So, load, because of the high inductance, the load will flow here IN DC, but because of this L and C, there is a resonant discharge of C or resonant charge of C in the opposite direction, through which path? The L and C. So, we will mark that one with a different color, so that it will be visible. So, apart from the load, there is a resonant current here. Okay. This resonant current, we will mark it as IR. Okay. So, how long it will? Because of the LC resonance, this capacitor will charge in the opposite direction. So, how the waveform will be? So, the resonant charging, the capacitor, the whole voltage and current waveform will look like this. So, the capacitor initially charged to E here, due to resonant charging, it will go like this and come to minus E here. So, part of a sinusoidal, that is, it will charge in the opposite direction. So, what will happen to the current? Current, if you see here, that's IR current, it will slowly increase. At this point, current is maximum. So, di by dt is minimum, then it will go like this. This is our IR. The moment current is 0, the capacitor, assuming ideal LC circuit, the capacitor will charge to the minus V here. So, this is our IR. Okay. Once the capacitor is charged the other direction, this capacitor is ready for commutation of S1 at any time. Now, this capacitor can, whenever we turn on this S2 here, whenever turn on this S2, now the capacitor is charged in the opposite direction, it will apply a reverse voltage across the thyristor and thyristor will switch off immediately. Now, this period we should note this one, this is the resonant half period. This resonant half period, if you see, what is the period? The omega r, the resonant frequency, omega r is equal to 1 by this standard circuit, 1 by root LC. Okay? 1 by root LC. Now, this is the omega r. So, what is the period? Half resonant period. Omega r is equal to if TR is the half resonant period, it will be 2 pi by TR. Okay? This is the half resonant period. So, 2 pi by omega r. So, TR will be equal to, you can find out, pi into root LC, because we know it omega r is equal to 2 pi into Fr, okay, and Fr is equal to 1 by TR. Now, why this period is very important? So, during the turn on process, this period half TR we are using for resonant charging of the capacitor in the opposite direction. So, what it means? This means, sorry, this is TR is equal to 2 pi. TR is equal to, sorry, I will again mark this one. TR is equal to here, TR is equal to 2 pi into root LC. Okay, this is the one. Now, this is very important. So, this much period we require for capacitor to resonant charging. So, once the capacitor is ready for commutation, that means capacitor is charged in the opposite direction, then only it will be ready for commutation, commutating the main thyristor S1, that is this S1, here is the S1, this S1. Now, so this period, resonant period is as small as possible. How much small? That will come to that one later for designing L and C. So, assuming the capacitor is charged, now it is ready for commutation. Now, let us take the condition when we turn on S2. That means we are ready for the commutation, and now we are turning on S2 to turn off S1. So, let us go to the next page. Here what will happen? S1 is turned on immediately. So, let us draw the circuit during commutation. Now, turn off period. That is turn off of S1, that is the main thyristor. Now, how the circuit looks? You have E here, S1 is turned on when S2 is turned on. So, the capacitor, the condition immediately S1 is turned on, it will look like this. Capacitor is in this direction charged. Now, S2 is turned on. So, S2 turned on, we will make it like this. The circuit is like this. You have the diode. See, diode is not at turned on. Why? When S1 is turned on, the capacitor voltage C, that is also equal to E, the capacitor voltage, the capacitor C, the voltage across the capacitor is E, then E. This 2E will come here at this point. Let us say this is A, at this A point, and diode is reverse bias. Diode will not conduct now. So, still load is highly inductive and load should get the full DC current. So, current cannot change in this inductance. So, still this DC IL will flow. That means this IL will come through C1, S2 and through L and go to the load. So, that current path we will mark now. The current path is like this. And returns. This is our IL, DC current. So, what it means? The capacitor will slowly discharge. Capacitor will be charged by a constant current IL. Now, or the capacitor will discharge then charge in the opposite direction. Now, the capacitor will be discharged with a constant current equal to IL, discharged with a constant current that depends on the load, that is IL. So, capacitor will slowly discharge, and again see till the diode is turned on, load cannot freewheel. Once the load freewheel, the commutator circuit is totally isolated. So, for the diode to be, this diode to be forward biased, this capacitor should charge in the opposite direction, that is in this direction to E through using IL. So, when it becomes E, it will oppose the input voltage E, and any slight overcharge, diode will be forward biased due to the capacitor. Then the diode will discharge. So, what will happen? Current here now the capacitor will be discharged with constant current IL. Then after that capacitor is discharged, again capacitor is charged to, capacitor will be charged to E, capacitor will be charged to E with the constant load current. So, then what happens? That once the capacitor charged to this point, that is this way, it will oppose E, and the diode, assuming very small difference voltage, diode forward bias very small voltage only required. So, diode will turn on and the load will freewheel. Load will freewheel through this path. Now, the commutation is complete. Okay. What happened to the capacitor voltage at this point? Capacitor voltage again it charged in the opposite direction. Now, you do not require the initial original that turn on circuit to charge the capacitor, that is this switch SW and R is not required to turn on the capacitor. Now, the capacitor reset will take care of the thing. How? If you see here, because of this load current. Now, how the capacitor condition will be? So, diode is, this is switched off, this is S1 here, capacitor is charged to in the opposite direction E, then you have the E here, this is E, this is also E. So, this is the circuit, it is ready. capacitor is charged, and again as when S1 is turned on, it will through resonance charging, it will charge in the opposite direction and it's ready for commutation. Now what is more important thing is how to find out this L and C, so that the resonance charging period is as small as possible compared to the T on time of the S1. Why? The output voltage depends on V0. From the buck converter we know V0 is equal to input E into T on divided by the total period T. So this is the way. So this T on, for a variable voltage, the output voltage depends on the T on. So the minimum duty cycle, so our resonant half resonant period TR should be much less than the minimum T on period. So one condition. Now, so one condition only there. Now we have two values to find out, L and C. So two condition is required. So how to find out the C? Let us start with the C. We have introduced the C in the circuit so that we can give a voltage, a force. We can force a voltage across the thyristor to switch off. That is force commutation. And we assumed during the previous analysis that the S1 switch S1 will commutate, switch on immediately. But in all practical circuit, the thyristor will take some finite turn off time. So this you can find out from the data sheet. So that means any thyristor will have a minimum T off time. So during the full T off period, till the thyristor is turned off, that is during the full T off period, we have to apply the reverse voltage across the thyristor C. So from this circuit, when T1 is turned on, the voltage across the C was this one, plus and minus here. Okay. Now due to the resonance charging, it will come to the negative voltage here. With the resonance charging, this negative voltage will come here. Now, when S2 is turned on, this negative voltage, which is marked with the blue color, will come across the thyristor, and the thyristor will discharge due to the load current. So this diode S1 will be reverse biased till this thyristor discharge from it will come from E to 0 through the constant DC current. So this much time we will be reverse biasing the thyristor. So for a circuit, the load current can vary. So if the load current is maximum high, the capacitor discharge will be fast. So for a maximum load current also, the discharge time should be more than the T off minimum of the thyristor. That means during discharging of the capacitor, during this discharging of the capacitor with constant load current, the discharge period, that means it is completely discharged to 0 period, that should be more than the T off minimum of the thyristor. So it will be capacitor is assuming this is the discharge period. Let us take the discharge period is equal to TQ. So TQ into I load maximum. That is, for any circuit, what is the maximum I load current? This is the total charge. This will be equal to C into E. So, I will say this is the load maximum current. That depends on the load. So, this is the equation. From this one, the TQ, the time required for the capacitor discharge fully from E to 0 voltage is equal to TQ is equal to CE divided by IL. CE divided by IL. So, from this one and the TQ should be more than the T of minimum. So, from that one, let us go to the next page so that we can make it clear. So, from the CE is equal to TQ, the discharge period, TQ into IL maximum load current. Load current can vary, we know the circuit, we know the load, maximum minimum load current should be known. So, for the maximum current, this TQ should be, what is TQ? TQ is equal to CE divided by IL. This TQ should be greater than or equal. So, greater, how much greater? That depends on the your design. You have to go back and forth and design. Okay, 10% more of the TQ minimum. So, depending on your design. So, there is no, here we cannot say exactly this one. This is the depends on the designer's capability, how to give a cost effective solution. But this is the approach. So, it should be greater than T of minimum. T of minimum, that is a, that will be specified in the data sheet. T of minimum for the main thyristor. For the main thyristor S1 from this equation. We can find out TQ. This is C. So, from this equation, we can find out from this equation, E is known, IL is known, T of minimum is known. From this equation, we can find out C. How? From this inequality, C will be greater than or equal to T of greater than or equal to T of minimum, that is the thyristor turn off time, divided by E into IL, I load maximum. So, first you compute this value and the value C chosen should be greater than this value. This will ensure your commutation. Now, there is another thing. Capacitor we have found out, there is one more component, L we have to find out. So, how we will find out L? Let us go back to our original circuit again. Let us go to the next page. See, during turn on, the moment S1 is turned on, the load current will flow, also the resonant current will be flowing through the main switch S1. That is, this is our E, main switch is turned on, that is this is our main switch, capacitor initially charged to this value, then you have the diode L. Okay. Here you have the load circuit. So, the resonant current which flows through C and L. So, we will mark it like this, that is this current IR. What is the equation for the resonant current for an LC circuit? This IR, we know it, IR is equal to voltage across the capacitor is E. So, E into root C by L into sin omega resonant frequency, that is 1 by root LC into T. So, this resonant peak current, that which we have drawn before, the current which go and the capacitor and charge the capacitor in the opposite direction. That is this one, plus E and minus E. This resonant current, that is this peak value is equal to E into root C by L. This value will go through the S1. So, during S1 on, the current flowing through the S1 are IL plus the peak current into root C by L. This is the peak current. This much peak current every turn on. For this will happen for every turn on. Every turn on. So, load current, that is the maximum load current, plus E into root C L by will go through the thyristor. So, this current, this E into root C by L is a small duration. So, any thyristor will have a repetitive peak current, that is repetitive peak current. Let us see that we will make it as IPR, repetitive peak current. Any thyristor data sheet will give this one. So, this data, so we should ensure that any time this repetitive peak current should be our IL plus E into root C by L, that is IL plus E into root C by L should be always less than or equal to the repetitive peak current, okay, or the resonant current E into root C by L should be less than or equal to IP minus IL maximum, load maximum current. Let us represent this as I0. Okay. So, this condition shows that the condition what you have written here, E into root C by L should be less than or equal to I0. What is I0? I0 is equal to repetitive maximum IP minus I load maximum. I load maximum. This is equal to E into E square into C by L should be less than or equal to I0 square. That means L should be less than or equal to E square C by I0 square. One condition. So, from here we found L should be or E0 square E0 square C by I0 square should be less than or equal, or L should be greater than or equal to this value. But that is not sufficient. There is one more condition we want to do it. Okay, from the resonance circuit we found that omega R is equal to 1 by root LC. Okay, this is equal to 2 pi into FR or 2 pi by TR, where TR is the resonant period. Okay, so TR is equal to 2 pi into root LC. But what we are talking about the half resonant period, because we are not allowing the current to, because of the diode we are not allowing the current to flow in the negative direction, the half resonant period. So, the half resonant period, is equal to TR by 2, will mark as TR dash is equal to pi root LC. Okay, and we want this half resonant period pi root LC should be smaller than the T of minimum, much smaller than, or the condition T of minimum required. So, to ensure we will say 10%. So, these are all design criteria, 10% of the duty cycle, minimum duty cycle. So, 10%, 0.1 of T on minimum. Okay. Let us square this one. That means pi square into L into C less than or equal to 0.01 into T on square minimum. Okay. This implies from this inequality what we can find out. L should be less than or equal to 0.01 T on square minimum divided by pi square C. So, let us go back to the equalities. That means L, this should be 0.01 T on square divided by pi square C. This is the condition. So, we can compute this value. E is known, C is known, I0 known. I0 is equal to IP minus IL. I0 is equal to this value. Okay. Then the T on minimum is known, that is this one, depending on the variable duty cycle, minimum chopper. Capacitor value we have initially find out from the T of minimum required to switch off the thyristor. So, from this value we can find out the maximum range of L and the minimum range of L. You have to choose L in between. So, computation will be Pakka. So, using simple rules, using engineering approximation, one approximation we said the load is highly inductive, so load is linear. So, from the linear charging or discharging period we have found out the T of maximum or T of minimum required for the capacitor to discharge fully, so that the thyristor will be reverse biased. We found out the C. Then from the repetitive peak, based on the resonant peak and the load current, one condition for L, one range of L we have found, the lower range, Then the upper range we found out the minimum resonant period. That should be much less than the T1 duty cycle minimum of the circuit. From this one we can find out the L and C, and the commutation is complete. So, with this that force commutation, we are only talking about the DC to DC converter. Just to introduce the DC to DC converter, to introduce this commutation, very widely used commutation circuit, popular commutation circuit. Okay. Now, what we want to do? The purpose of this introducing this force commutation, what we want for a PWM operation of the thyristor, so that we can have unity power factor from the mains. So, unity power factor, at the same time the converter should be able to work in the 4-quadrant region, so that power flow can be from the input to the load, from load to the mains. So, what is the basic configuration for a 4-quadrant converter? Let us start. Let us talk about the converter, a front end AC to DC converter with the unity power factor. At the same time 4-quadrant operation is also possible. Let us talk about how we can have a converter with 4-quadrant operation. Converter we can be used, that is converter, AC to DC converter. So far we are talking about AC to DC converter with 4-quadrant operation. Okay, we talked about our basic DC to converter previously, that is the buck converter. The configuration is like this. You have this one, then the inductance, you have the load, freewheeling diode D here. Okay. This is our E. Now, we are not showing the commutation circuit. Commutation circuit is inside, it is there. Okay. Here, if you see here, because of the thyristor, main thyristor S1, we will do with a different color. Because of this thyristor S1, the load current can conduct only in one direction. Okay. That means this output voltage can vary from 0 to positive only, and current only one direction. So, if you see the power diagram, that is E0 versus I0, let us say load current I0, E0 versus I0, only one quadrant is only possible, single quadrant operation. This is E0 and this is I0. Now, we want a power flow from load side to the source side. So, from the buck converter we know that E0 will be less than E always. E0 will be less than E. Okay. Now, to want a power flow from E0 side to E, that is power flow from E0 to E. What is the configuration? We know the boost configuration. This is buck, this is buck. You know the boost configuration. So, how do you draw the boost configuration? Now, the source is our E0, the power flow is from the load side to the E. So, let us draw our load side like this. So, how do you boost it? First, any boost circuit we know that inductor is charged first. So, here is our thyristor. So, we are using thyristor here or IGBT or MOSFET, you can use it. So, since so far we are talking about thyristor, we will talk about the thyristor now. So, this is one. So, you initially this is the main switch, S1 is turned on. When S1 is turned on, full E0 will come across L. When S1 is turned off, what will happen? We will put a diode here. This is our E. When S1 is turned off, the current will flow through L and D. That means the current flow when S1 is turned on. S1 is turned on, the current flow will be, it will flow from, because of the stored energy in the inductor, it will flow from this side to this way. So, that what is mean by that one? Here we are not changing the polarity of the voltage, current direction we have changed. So, we can have two quadrant operation. Voltage is still positive only possible. So, we can have two quadrant operation. Okay. Now, this two, so for one quadrant we use buck converter, for the two quadrant we use other converter. Can we combine these two so that the circuit can buck as well as boost? That means, or from the power flow point we can have power can flow in both direction. So, let us draw that one. See here, so now we are going to combine these two. So, what we want, the numbers we will change it. This one we will make it S2. These are main tester, other one is S1. So, how the circuit will be? So, E is still E here. This is our E. This is our old S1. Okay. S1 come here. This is our load. Okay. The freewheeling diode. This freewheeling diode is this one. Okay. Now, for boosting, S2 is connected between inductance this side and the load. So, this is here. Same way, we can use it here, S2. And the diode, this diode will come here. This will make it D2, this is make D1. So, if you see here, to make the buck and boost independently, we will color it here. This is S1, oh sorry, we will color the different color. This is S1, this is the D2. These two are for boosting action. Okay. So, we can have two quadrant operation. So, if you repeat the same thing other side, we can have 4 quadrant operation. So, the circuit here will be, final circuit will be see, I will connect the diode like this. This side also it is there. Okay. Now, this point we will remove and connect it here. So, the load will be like this. So, what it shows, the quadrant operation here, we can have any operation from this side, we can have negative operation also. So, we can all 4 quadrant operation is possible. That means both voltage and current, as far as the load is concerned, both voltage and current can be positive as well as negative. Okay? So, this can be used. This configuration is called the 4 quadrant chopper. So, if you know, this is a single phase inverter configuration. See, now the load we want both positive and negative. So, load will have alternating current and voltage. So, if you say positive and negative means we can PWM operation is possible. So, if you go to the next page here, sorry, we want the load both positive and negative. So, positive waveform and negative waveform. Okay. So, I put sinusoidal voltage. Is it possible? See, with the duty cycle control, I can have variable voltage. At very many instants, I can have different voltage. So, that I can have a sinusoidal voltage. At the same time, I can have a sinusoidal current also. That means both positive and negative is possible, like current. Something like this is possible. Now, for unity power factor, the current here should be like this, unity power factor. So, AC to DC converter, where we are talking about AC to DC converter. So, this is the DC, this is the AC part. AC to DC with unity power factor, is it possible? We will try to study that part in the next class.